Hello and welcome everyone to the Varsity Tutors STEM Success Series, where I hope you are ready for a whirlwind class today. That's right, be ready for a lesson full of twists and turns, but mostly twists and really twisters. We are going to examine the wild world of tornadoes, and we've got the perfect teacher here for you today. While most of us, when we hear that tornado siren, rightfully head for shelter in a basement or at least a room without windows, your teacher for today, Storm Chaser Dr. Reed TIMMER, gets in his Dominator vehicles and heads right toward them. So there's no one better to teach us what it's like to be right in the middle of a tornado. And we'll learn quite a bit today about one of nature's wildest and most amazing types of storms. Now, before I turn it over, Reed, just a couple ground rules so you get to know the classroom and know what to expect. One, this is not a class for fair weather students. We want to see a flurry of activity. So please ask Reed as many questions as you have, put your name on them, and we'll make sure that we can interview him at the end of the class and get as many answers as we can. So use the chat panel to the right for that, to ask him questions. Also use it to answer his questions. He's going to ask you a few things to see, your experience with tornadoes or your opinions or what you've seen before. And so use that chat panel and the polling tool at the right to answer Reed's questions and to ask him some of your own. Also, make sure that you've got a camera nearby, because in about a half an hour, we're going to give everybody a chance to take a cyclone selfie, so to speak, with Reed and some meteorological equipment so that we would use to predict and really better understand tornadoes. If you take that picture, so again, make sure you've got a camera nearby and upload it to Instagram, you'll be entered to win a Wild Wacky Weather Kit and a free year membership to VT Plus. Now, VT Plus is a Varsity Tutors class subscription service where if you don't win, for $19 a month, you can take classes on just about anything from math to magic, from storms to science projects and everything in between. So great prize, have that camera ready. And when you get it up on Instagram, we'll have the instructions at the end of class to tag Reed TIMMER and Varsity Tutors for your chance to win. All right, with all that said, I've been looking at the forecast because Reed has taught me well. It's partly cloudy with a 100% chance of fun. So please welcome your teacher for today, Storm Chaser, Dr. Reed TIMMER.
Hello, everybody. Thank you so much for joining us here tonight. We're going to be talking about all things tornadoes. I've chased over 700 tornadoes over my 20-year career. I started storm chasing actually when I was 16, right when I got my driver's license. And I've even been inside many tornadoes with our armored vehicles called the Dominators. So I'm going to tell you about all the different shapes and sizes of tornadoes, how that feeds into the life cycle of these supercell storms. I'm also going to tell you about supercell structure as well and what it takes to try to get close to these tornadoes in a supercell structural sense. I'm going to tell you about the ingredients that come together to produce these tornadoes as well. We're going to talk about multiple vortex tornadoes. We're also going to talk about forecasting these tornadoes and what it takes to try to find those regions where severe weather can happen. And of course, we're going to talk about tornado safety. And this is a video of some very close range tornadoes as we've been intercepting these with our armored vehicles called the Dominators, and definitely focus on the shape of those condensation funnels. Here you can see that big funnel. That's basically cloud matter, basically like a massively rotating fog bank that's associated with very strong, potentially damaging winds. This right here is an EF3 tornado. That was a very large wedge tornado about a quarter-mile wide in northeastern Nebraska. But the shape of that condensation funnel doesn't necessarily tell you where those strong damaging winds are located. The tornado can be much wider than that cloud matter. You can see that debris going around that tornado. This tornado actually extends out much wider than that cloud matter that you can see there. And also these tornadoes have a tendency to split up into multiple vortex tornadoes. But when you're watching these videos, imagine a giant vacuum cleaner above them. That's that thunderstorm updraft that is rotating. That's a supercell storm. And when you get that massive vacuum cleaner above these tornadoes, it can stretch those tornadoes and intensify them, almost like a figure skater. When they pull in their arms, they spin faster. That stretching motion from that large vacuum cleaner of a supercell updraft causes these vortices to become very compact and intense. The winds inside these tornadoes can be well in advance of 200 miles an hour. And when they split into those compact multiple vortices, the wind speeds inside there could even be 500 or 600 miles an hour on the really, really small scales. And that's why you'll see one house that could be completely damaged, whereas the one next door can be untouched. And there are a lot of complexities within these tornado damage paths. And a lot of that is caused by the tornado funnel interacting with the friction of the earth. This tornado comes down from the sky or builds up from the ground up. That is a source of debate as to how tornadoes form. We're going to talk about that later on in these classes. But this tornado right here definitely had winds likely in excess of 200 miles an hour. And when that vortex interacts with the friction of the earth, it can cause the wind to go in toward the center of that low pressure. And if you can imagine a giant, really deep low pressure at the center of that tornado, that's really what drives the winds around it. There are massive gradients to those isobars, to the pressure, and that's what drives the wind in a cyclonic fashion around these tornadoes. They spin counterclockwise here in the northern hemisphere. They spin clockwise in general in the southern hemisphere, related to the shear profile as you go up. But we're going to break down what causes those crazy tornadoes and talk about what it feels like inside of them. And now let's start off with a quick question. Which of the following is not a type/shape of a tornado? These are all general shapes here. One of these is not a traditional shape of the condensation funnel. I'll get some good answers coming in. Stovepipe, rope, elephant trunk. Many of you have probably heard of these terms in storm chaser videos. And actually the correct answer here is C, witch's hat tornado. You could probably use that term to describe a shape of some condensation funnel, but really these different types of tornadoes describe the shape of the funnel as it's coming down, and they also relate to the life cycle of the tornado. As they develop, they touch down, usually as more of a cone, will get wider, and then usually at the end they rope out. But we're going to break down every single one of these different types of tornadoes in the subsequent slides. But first, we'll talk about what is a tornado. A tornado is really a rapidly rotating column of air that extends from the cloud base all the way to the ground and can be associated with damaging winds at the surface. But really it is just that rotating column of air making contact with the ground. The condensation funnel doesn't have to be all the way to the ground. Here you can see a tornado causing power flashes, definitely violently rotating at ground level, associated with some condensation as well. But sometimes the funnel itself can be elevated above the ground, and then you'll get a dust whirl underneath it. So that condensation funnel or the cloud matter doesn't have to go all the way to the ground for it to be called a tornado. You just need that rotating closed column of air extending all the way to the ground from the base of a cumuliform cloud. A cumuliform cloud is basically a convective cloud. A cumulonimbus is those giant thunderstorm clouds that we talk about. A supercell storm is a type of cumulonimbus. So a tornado needs to form underneath convection such as this. And a tornado doesn't only have to be a supercell tornado like this one. It can also be fair weather water spouts and even land spout tornadoes, those dusty tornadoes that are connected to the base of the cloud, but not necessarily associated with a supercell storm. But the strongest tornadoes that you hear about every spring and summer and throughout the year, and actually tonight, as there's a severe weather threat across northern Mississippi into central Tennessee, those strong damaging tornadoes are those that are associated with supercell storms or a thunderstorm with a rotating updraft. And now we're going to break down the different types of tornadoes and then relate these to the life cycle of a supercell. This is the wedge tornado, the most infamous of all tornadoes. And a wedge tornado is named after the shape of the condensation funnel, as I mentioned, being wider than it is tall. Wedge tornadoes are often the strongest tornadoes as well, and the most likely tornado to split into multiple vortices and really pack a punch with those wind speeds. One of the widest wedge tornadoes, or the widest wedge tornado in recorded history, was over 2.5 miles wide, and that was a tornado outside of El Reno, Oklahoma, back in 2013, May 31st. Very violent, large tornado. And a tornado that's 2.5 miles wide can split into miniature tornadoes that can be up to a quarter mile wide as well. I chased that tornado there in western Oklahoma and El Reno. I also chased the second widest tornado in history. That was near Hallam, Nebraska in 2004 at over 2 miles wide. These wedge tornadoes can be very dangerous. They can really leave large swaths of damage as well. That's the dark side that these tornadoes leave behind, is the damage that they cause at ground level. Many times these tornadoes can happen at night as well. Nighttime tornadoes are definitely the most dangerous, but these wedge tornadoes here are the widest. They're wider than they are tall, and definitely capable of the greatest damage. And this is a stovepipe tornado. I believe that this is capable of the strongest wind speeds because of how compact the winds are within a stovepipe. And a stovepipe is defined with a condensation funnel that is similar in width from the cloud base all the way down to the ground, but still a robust size to that condensation funnel. And typically when tornadoes develop, they come down as a carrot or a cone tornado. Then they gradually expand. They expand into a stovepipe tornado, or they can go straight to a wedge phase and then constrict into the stovepipe, as you see here. And that's usually when you get the strongest wind speeds inside of a tornado. I've also seen these stovepipe tornadoes split into multiple vortices as well, which definitely is an obsession of mine as we're trying to intercept these tornadoes directly and measure those really strong winds inside. But this is a classic stovepipe tornado, usually a signal that that tornado has reached maturity with the supercell. This is the textbook elephant trunk tornado here. It's not quite a rope tornado because it has a thicker condensation funnel, but that condensation funnel looks exactly like an elephant trunk as it goes down to the ground. This was a tornado that I intercepted near the Denver International Airport here, and you can see as it meanders horizontally, that has some cold stable airs undercutting that funnel and causing it to stretch horizontally before it bends down to the ground. But this was in the high plains of eastern Colorado. I chase anywhere from Tornado Alley to Dixie Alley, the Deep South, really anywhere there are chances for tornadoes. But I also chase quite a bit in the high plains there of eastern Colorado and eastern Wyoming. And often you see these beautiful tornadoes like this. But these tornadoes can also be damaging. Usually an elephant trunk tornado is just before a tornado is about to enter the dissipation phase, when that funnel starts to constrict and get smaller and smaller. So usually an elephant trunk tornado is a signal that the tornado is past maturity and starting to head towards its weakening phase. And here's some video of that elephant trunk tornado. You can see that the funnel initially is shaped like a cone. And notice how that condensation funnel is above the ground. That doesn't mean that this isn't a tornado. There's very likely a ground circulation underneath this, a closed column of rotating air all the way down to the ground. This is already a tornado, but you can see that condensation reaching to the ground. One thing in the atmosphere is that the air can condense more easily at lower pressures. So that right there, that cloud matter that's reaching down to the ground, that shows you that there's a channel of low pressure reaching down to the ground, and it's also driving wind around it. Above this tornado, the mesocyclone, basically a giant vacuum cleaner stretching it into the vertical, making that vortex even more compact. But you'll see this tornado basically mature into an elephant trunk tornado, and then it begins its dramatic rope out phase, which is when the tornado is dissipating. And this is the textbook rope tornado. Anytime you're out there storm chasing and you see a rope or it looks like the tornado is dissipating, a lot of times the tornado is not done. And you can get beautiful rope outs like this on the backside. This is a tornado that is toward the end of its life cycle. The way that these tornadoes generally form is that dry air sinking on the backside of the supercell wraps around the low-level mesocyclone, enhancing the vorticity on the north side of that, or the spin in the atmosphere. And when that migrates underneath that mesocyclone or the vacuum cleaner, it stretches that tornado, keeps stretching it. And then as that dry air wraps around it, that also aids in the constriction process. And eventually that dry air wraps completely around the tornado and then chokes it off completely from the parent updraft of the storm. And when that happens, the dissipation phase begins very, very rapidly. But sometimes these rope tornadoes can also be more intense than earlier in their life cycle. And that's because that spin gets more and more compact. And then through conservation of angular momentum, the spin has to continue whipping around. And a tornado doesn't only have horizontally rotating winds, but there's also rising motion often near the center of the vortex. And so the damage that's caused at the ground isn't only caused by those rotating winds, but also the violent updrafts that you can get inside these tornadoes. And as I mentioned, the multiple vortex tornado is yet another type of tornado. And usually the wedge tornadoes are more likely to split into those multiple vortices. And this happens when the low pressure at the center of the vortex becomes so intense that it can't maintain force balance of those winds anymore around the vortex. And especially right near the ground where the friction of the earth can slow down that flow just a little bit. The air goes in toward that low pressure. We call that cross isobaric flow. And when that wind goes in toward the center of the tornado, it can cause it to split up into these smaller tornadoes called subvortices. And these subvortices are where some of the strongest winds at ground level can happen anywhere on the planet. And wind speeds inside these subvortices really have not been measured. Overall, I've been impacted by a couple of these while intercepting tornadoes in the armored vehicle. But that orange color that you see in Dr. Fiedler's work from many years ago shows you that the strongest wind speeds inside these subvortices happen right at ground level. And they could be up to 2 to 4 times that of the main tornado. So if you have an EF5 tornado with winds of greater than 200 miles an hour, theoretically, inside subvortices, if it splits into a multiple vortex tornado, the wind speeds could easily be 400 or 500 miles an hour inside there on the really small scales. And that's why you'll see such terrible destruction inside these damaged paths, whereas a house directly next door can appear as if it's untouched. And here's a multiple vortex tornado, one of the most infamous tornadoes to ever happen. This is actually the birth of the widest tornado in recorded history. Initially, it wasn't as wide as it was at maturity. Eventually, this thing kept growing, eventually reaching over 2.5 miles wide in width. And the individual subvortices that you can see there, basically miniature tornadoes that are spinning around inside like a merry-go-round inside the parent vortex. Some of those reached a width of even 1/4 mile wide, which would be extremely wide for even an individual tornado. But this was an incredibly wide tornado in western Oklahoma, 2013, May 13. And you can see just how complex the circulation is at ground level. When I'm intercepting tornadoes, many people ask me what it's like inside of a tornado. Many of them reference the movie Twister, where Bill Paxton and Helen Hunt were looking straight up through the tornado at the sunny skies above, almost like an eye in the middle of the tornado. It's really nothing like that in the middle of a tornado. It's chaotic. You see fog all over the place, dirt blowing around. Your ears are popping from that extremely low pressure fall inside. I've ruptured eardrums inside of these tornadoes, but it is just an incredibly chaotic, powerful experience inside of a tornado. And now this is the life cycle of all these different shapes of tornadoes that you may have seen. I took these from a couple of different tornadic supercells. Initially, you start to get a wall cloud, which is basically a lowered cloud element beneath the cloud base of the storm. You can see that sharp horizontal line there to the cloud. That's the base of the updraft, basically the base of a rotating updraft above it, that giant vacuum cleaner, just this constant source of suction up in the cloud. And then when you get a smaller little vortex or an area of spin underneath it, it can get coupled with that updraft and instantly become a tornado. The wall cloud will often cut into a carrot shape. That's the cone tornado, number 2 there. Number 3 is the stovepipe. So that cone will continue to expand, get very compact all the way up to cloud base, the same width. That's the most intense portion of the tornado when it's a stovepipe. Number 3 and number 4 was a tornado that I saw near Dodge City, Kansas, just to the south of there in 2016. An EF3 tornado there that likely would have been rated higher if it did more damage out there. Thankfully, that was a relatively rural area there in western Kansas. But then the tornadoes can mature into the wedge phase. Number 5 is a wedge, wider than it is tall. You can see that low-level tornado cyclone above it. A lot of vertical motion happening there as well. And then the tornado can constrict, becoming a dramatic rope out. And number 6 shows you the rope out phase of that condensation funnel. And really in a matter of seconds, it goes from that to just completely disappearing into thin air. And that tornado right there was unique because it dissipated and completely disappeared. And I was sitting there just to its south, and then bam, suddenly a rope appeared and took down all of those power poles just as it crossed that north-south road to the south of Dodge City. But this shows you the typical life cycle of tornadoes, beginning as a wall cloud, then the cone funnel. Sometimes they'll go straight to the wedge phase and then constrict into a stovepipe and then further constrict into the rope. But generally speaking, tornadoes like to follow this blueprint of evolution from development to maturity to dissipation. And here's a time lapse of that same tornado showing that rope out process. And also watch just to the northeast of that tornado. I'm looking north and look at that wall cloud spinning to the northeast of it. That's a new tornado that's about to touch down. This shows a cyclic supercell, the tornado right in front of me, reaching maturity. Big stovepipe there, starting to constrict into a wedge. You can see a couple other storm chasers out there. Playing hopscotch to the south of this tornado. But look at that new wall cloud just to the northeast of it starting to rotate. And you're going to see that stovepipe continue to constrict until it becomes a rope. You can see that farmhouse just to the west of it that thankfully wasn't hit by that tornado at its most intense phase. But there you can see two tornadoes in the same frame. The new one touching down to the northeast. The one just to my north is roping out. And we're going to talk about this handoff process, or how supercells can be cyclic, producing one tornado after another. When one tornado ropes out like that, just disappearing, the new one will often form to its northeast if the conditions stay the same and are still favorable for tornadoes. And here are the twin tornadoes. This is an example of the handoff process that happens if the environmental conditions are so extreme that a tornado, the process from maturity to rope out takes a little bit longer. That tornado can remain, and then the new one will touch down, leading to what's called twin tornadoes, but two separate tornado cyclones associated with the same mesocyclone. And this one was from 2014. This is Pilger, Nebraska. The town of Pilger sustained EF4 damage. And in this case, there were two violent tornadoes on the ground at the same time, two EF4s. And it actually happened a couple different times throughout this supercell's life cycle. It actually produced an EF4 tornado just prior to this. Then these two were on the ground at the same time. Ideally, we would continue to chase these twin tornadoes. But when we saw this damage, as a storm chaser, you drop everything, you help out in the rescue effort, going house to house, trying to find people in need. And that's just what you're supposed to do as a storm chaser. If you come across damage, that's what we do, is help out in the recovery effort. But you could definitely see here very clearly the dark side that these tornadoes leave behind. And that is the very severe damage that we see every year across Tornado Alley and Dixie Alley. And that damage is described by the enhanced FUJITA scale, or the EF scale. This was derived from the FUJITA scale by Dr. Ted Fujita, the most famous tornado scientist of all time. He broke down and surveyed so many different damage paths that he was able to come up with these damage indicators and relate those to estimated wind speed. So the enhanced FUJITA scale was derived from the F scale, but it factors in the engineering of the structures. There are 8 degrees of damage, 28 different damage indicators that factor in engineering, from mobile homes that may have anchor bolts to very well-built 2-story homes, brick homes. There are also vegetation indicators as well. The National Weather Service is the only federal agency that can issue official EF ratings. And this was actually an EF4 tornado in northern Mississippi. And you can see just that terrible destruction out there. Mobile homes that were completely ripped from its foundation. An EF5 tornado is capable of ripping a well-built home completely off of its foundation with no debris left behind on that foundation. An EF4 can do the same, but leaves a little bit of damage scattered on that foundation. And it goes all the way back to the EF0 with winds of 65 to 85 miles an hour. You probably could drive through an EF0, but they can intensify from EF0 to a violent tornado in a matter of seconds. But an important thing to note here is that the enhanced FUJITA scale is based purely on damage. There's no way to get a real-time estimate of the wind speeds at ground level inside of a tornado. So you really have to survey the damage and then derive those wind speed estimates afterward. And the estimated wind gusts that are derived are 3-second wind gusts, which is also different than the standard 1 second. And now we got another question as we're heading into section 2, supercell structure. I'm going to tell you guys about the hook slice maneuver, how to punch through a hail core, and where is the safest spot to view a tornado as well. But we're going to break down it all relative to supercell structure. But first with a question, what is a supercell storm? And we've already talked a little bit about what the supercell storm is so far in discussing the tornadoes, but the supercell is the most important part for the development of these strong tornadoes. I can see some good answers coming in. It's definitely not the convergence of two tornadoes coming together. That's called big problems when that happens. It's definitely not a tornado that touches down over water. That's a water spout, a thunderstorm. It is a thunderstorm that's accompanied by high winds, but there are many different types of thunderstorms that can have those high winds. The correct answer here is B, a storm with a deep rotating updraft. And that rotating updraft, or that giant vacuum cleaner that we've been talking about, when it starts to rotate, it becomes a mesocyclone. And when you add that rotation to the updraft strength is even stronger, and it can accelerate in the vertical motion. And it makes it possible for these mesocyclones to suspend giant hailstones inside the updraft. They continue to circulate around inside that rotating updraft, accumulating layer upon layer of ice until they can even get up to 4 to 5 inches in diameter. And then they crash to the ground, blowing out my windshield and other storm chasers on the ground, causing substantial crop damage as well. But all of that is because of this rotating updraft called a mesocyclone there. And when the conditions are sufficient at the low levels, that mesocyclone can tighten into a tornado. You can see a tornado trying to develop there just on the north side. But the tornado exists on a smaller scale than the updraft above it. You really need the mesocyclone to tighten up below cloud base, and that depends on other storm scale processes that happen with a supercell storm. A lot of it's related to the sinking air on the backside of that mesocyclone. But this is a textbook mesocyclone in northeastern Nebraska. Sometimes we call these pancake stacks for obvious reasons. It almost looks like a stack of pancakes on top of each other. We often call them mothership supercells because they look like a giant UFO about to come in for landing. But usually when you get a supercell storm and a rotating updraft like that, capable of producing large hail, it's also likely capable of producing tornadoes. And this is an image that I put together over the last week. That radar image in the background is reflectivity. So that shows where the rain and the hail are falling. And this is a perfect supercell there that you can see. This is from the super outbreak in 2011 near Tuscaloosa, Alabama. This tornado was an EF4 tornado, probably could have justified even an EF5 rating with this event. But you can see that blue egg there that I drew. That's called the hail core. That's also called the bear's cage in storm chasing. That's probably the most dangerous place to be with a supercell storm. That's where you get giant chunks of ice, baseball size, softballs falling from the sky. The tornado can be just to your south, often backlit by sunshine as well. So when you hear storm chasers talk about punching the hail core, they're usually driving from north to south through that blue region. Sometimes you'll blow out your windshield. Sometimes the hail is too large and it can completely abandon the storm chase. Sometimes that hail can be so large it can even fall through the roofs and cause substantial damage. Farmers have to deal with that hail all the time, causing massive destruction. But the mesocyclone is just on the south side of that largest hail zone, directly above the tornado. You can see the hook echo in this supercell. That causes the rain and the hail are wrapping around the backside. If you're approaching the tornado from west to east, punching through that hook, that's called a hook slice maneuver. If the tornado is doing so much damage that it lofts that debris in the air, it can have a debris ball as well that shows up on radar. You can see that little bulbous area right at the end of the hook. That's actually that EF4 tornado happening. And the two gray zones are the downdrafts of the supercell. So basically a thunderstorm consists of an updraft and a downdraft. And when that updraft is rotating, that means it's even stronger as well. And the downdraft, or where the rain and the hail falls, can be separate from it. So downstream, you get the forward flank downdraft. That's where a lot of the rain and the hail falls to the northeast of that mesocyclone or east of the mesocyclone. And then on the backside, you also get sinking motion. Imagine this massive vacuum cleaner of upward motion. You usually have sinking motion around the periphery of it, and that includes on the back side of it. We call that the rear flank downdraft, or the RFD. That sinking air tends to dry out and then wrap around the south side of that mesocyclone. You can get damaging westerly winds there just to the south of the tornado. If you're approaching the tornado from the south, sometimes it can be concealed by that dust. Sometimes the rear flank downdraft can have a little bit of rain in it as well and conceal your view of that supercell storm. But in this case, the upper level winds are out of the west-southwest. See that arrow with the jet stream winds? That's way above the ground, probably 5, 10, 20, 30,000 feet up there. And those are the winds that take the rain and the hail in that updraft and deposit it downstream in the forward flank downdraft. And often, just like a rock embedded inside of a river or a creek, with the flow of the creek moving around it, you'll get two counter-rotating wake eddies downstream of that, almost like the supercell is like a rock in a stream, and the stream is the jet stream out there. You can get those two counter-rotating eddies, and that gives you what's called the flying eagle configuration. Notice how this thing looks like a flying eagle with two wings downstream, the eagle head there curled around by the hook echo. That's how you know you're dealing with a textbook organized supercell with tornado potential. And here's a visual rendition of that supercell map. The one I just showed you is looking down at the supercell storm through radar. This is out in the field looking due north at the same supercell storm. That rear flank downdraft we talk about will often look like a big shelf like that. You can see how it's laminar, almost like a pancake stack itself. That rear flank downdraft is surging from west to east. And you can see the clear slot on the other side of it. That's that drier air that's wrapping around the tornado, even enhancing the spin that much greater. So then the big vacuum cleaner above it, that is the supercell mesocyclone, stretches that tornado as it intensifies. You can see the wall cloud in this map. That's probably the new tornado that's about to form, whereas that tornado back to the west of it appears to be wrapped in rain. So this is a classic HP supercell. We're going to talk about that next. But look at those inflow bands. That shows you the southeasterly, warm, moist wind flowing into this supercell storm. That's what fuels that updraft, is the heat and moisture at low levels. Cold air above it triggers that updraft. The RFD wraps around, consolidates that rotation, and then you get a tornado. Here's another example of that mesocyclone. So really you can think of a supercell storm as an updraft. That's what you're looking at right here. See that sharp horizontal line just above the ground? That shows you the updraft base of the storm. So you have a lot of rising air. That rising air cools, hits its dew point and condenses, and that's the base of the storm. And then you can start to see it rotate as well. So not only is there upward motion, there's also spin. You can see all the lightning there as well. That's caused as small hailstones are lifted up in the updraft, and those small hailstones or grapple can also be charged. They can have an electric charge, and they lead to the charge separation. The more grapple you pump up into the storm, the more charge separation you get, and that triggers very frequent strobe lightning like this. And that happens when you have a very strong rotating updraft, because the flux of all that small hailstone vertically from lower to high is maximized with a strong rotating updraft. This is the one that was also in the high plains of Colorado here with a tornado warning. But definitely when you view these mesocyclones in a time-lapse sense, you can certainly see it's a combination of rotation and vertical motion. And here's another look at a supercell from the south. You can see that pancake stack mesocyclone above it. That's the updraft. That's a giant vacuum cleaner above it, the wall cloud below. And anytime you get a little bit of spin below that mesocyclone, it becomes a candidate that can be stretched into the vertical. And just like a figure skater, when they pull in their arms and spin faster, you constantly have that stretching action when you have a well-developed deep mesocyclone above it. And then the rain and the hail falling downstream on the north side of it. The bear's cage, as we mentioned, is just on the other side of that wall cloud on the north side of it. That's when you're storm chasing. You can get those giant chunks of ice, baseball or softball size, coming out of the sky. It's extremely dangerous up there to the north of the tornado. And up there in the bear's cage, you're often in the path of a tornado that's moving southwest to northeast. So this is the wall cloud. We've mentioned this a couple different times. This is usually the first step of tornado genesis, but this rotation is on a slightly smaller scale than the larger mesocyclone above it. So as that mesocyclone is organizing, that vacuum cleaner continues to intensify. Then it starts to pull a little rain-cooled air from the core, from the forward flank downdraft underneath that updraft, and that causes a lowered cloud element called a wall cloud to form underneath that cloud base. A wall cloud doesn't have to rotate, but when it starts to rotate, that means that it's got some tornado potential. The clear slot or the rear flank downdraft is wrapping from west to east on our side of this thing. This is a wall cloud up in Canada in 2007 that eventually became an F4 tornado, violent rotation. And just seconds after I snapped this photo, it had a ground circulation and dust swirls started to form underneath it. That's when it became a tornado. But anytime you see a wall cloud like this with that flat updraft base, this likely has a chance of producing a tornado, especially in a strongly sheared environment. This is another rendition of the supercell looking from south to north. So the last couple of photos you saw were real supercells, and this is a cartoon that describes the motion that's happening there. You can see that sinking air on the backside of the mesocyclone. The mesocyclone is that big red updraft. Usually the mesocyclone is tilted, almost like a tilted vacuum cleaner. We've launched rockets into tornadoes with trackable sensors and have tracked them as they fly through the tornado and the mesocyclone above. And we've shown that that mesocyclone is a lot more tilted, especially in those supercells in very dynamic environments. Sometimes it can be relatively vertically oriented as well, given storm relative shear. But that sinking motion on the back side of that mesocyclone, that's called the rear flank downdraft, and that wraps around the tornado, tightening it up within. But you can certainly see how the tornado exists on a much smaller scale than that massive rotating updraft above it. Mesocyclones can exist usually about 5 to 10 kilometers in diameter, sometimes a little bit bigger than that. The tornado below it, usually on the order of a kilometer or a mile, or even a little bit less underneath. You can also see those inflow bands showing that warm, moist air flowing into the mesocyclone from the east. We definitely saw those in those last images as well. And then you see the forward flank downdraft right there. That's where a lot of the heavy rain and the hail falls. But the largest hail falls just on the north side of that mesocyclone, and that's called the Bear's Cage. We also mentioned low versus high precipitation supercells, LP or HP for short. Usually supercells will develop as an LP or a classic. A classic has a combination of LP and HP characteristics. But notice on the column on the LP, that mesocyclone or the pancake stack above it is completely clean of rain. You can see the whole updraft base. You can see the wall clouds forming underneath them. If there was a tornado underneath that mesocyclone, it would certainly be visible. But then look at the right column. You can see a lot of rain and hail wrapping around the mesocyclone. The top one almost looks like a wedge tornado, but that's actually rain and hail concealing the entire low-level mesocyclone there. HP supercells are the most dangerous types because they can have a tornado that's completely concealed inside that rain. And then you get an HP supercell at night, and it's certainly very difficult to see. And if you're chasing at night, it can be incredibly dangerous. Sometimes you have to go purely by wind direction alone out there. And that's why storm chasing should only be done when you really know what you're doing, or it can be incredibly dangerous out there. But those HP storms on the right column, those are supercell storms that are wrapping in that rain and hail to the mesocyclone. And usually a supercell will transition from LP to classic, kind of an average between the two, and then over to an HP storm. And sometimes that can be triggered by moving into an environment with greater moisture, maybe a little bit less wind shear. If the environment changes, usually the personality or characteristics of the supercell will also change, but they also evolve and have a life cycle themselves. Sometimes they retain certain characteristics that they have throughout their life cycle. Other times they're not. Supercell storm is almost like a living, breathing organism, the perfect balance of inflow and outflow, almost like it's respiration, but they're so organized, incredibly organized beings. The balance of inflow and outflow, warm, humid air flowing into them, the downdraft on the backside, and those ingredients have to be perfect to come together to produce tornadoes. And now we're going to talk about what it feels like inside of a tornado. I've intercepted over a dozen tornadoes being right in the middle of a tornado, including an EF3 tornado inside the Dominator, our armored vehicles. The strongest wind speed I've ever measured inside of a tornado is 155.2 miles an hour inside a tornado in eastern Wyoming. And that's about all the winds that the Dominator can handle. But inside of a tornado is a little bit different than you might think. It's not like the movie Twister. It's chaotic inside. But what do you guys think it feels like inside of a tornado? A lot of good answers coming in, and we are going to show you exactly what it feels like inside of a tornado. I'm going to show you some video inside there as well. But in the middle of a tornado, it's quite chaotic. Here's a video from 2009.
We're in it almost. That's right. Yeah. Oh, wow. Maybe I should shut the window. What do you think? Yeah, window out. Right in front of us, Chris. Look, we're in it. Ears popping. Oh, low pressure. Scanning radar. We're inside it right now. Look at this. Look around, man. It's awesome. All right, it's right left. All right, we gotta get out of here.
But right when that happened, that was actually a sub-vortex that was impacting the vehicle. And that was when the wind spiked up to nearly 140 miles an hour that we measured in the Dominator. But this is a camera that's installed on the roof of the Dominator, the bubble camera. See that closed rotation there, ground circulation, a little bit of condensation there as well. Some elements of fog ripping by. And then on the backside of the tornado, one of those sub-vortices that I told you about flung around the backside and impacted the Dominator, blowing the window out. We normally had protective Lexan windows that we would lift up, but in this case, we didn't have enough time to manually latch those windows. The radar engineer in the back seat, his ears actually had a little stream of blood coming out of it because he ruptured his eardrum from the massive pressure fall inside that tornado. And that's what accelerates those winds around that low pressure. But our point in intercepting those tornadoes with our specifically engineered vehicles for withstanding those winds, our goal was to record data inside tornadoes that other people can't safely collect. I mentioned that there is a major lacking of direct measurements inside those suction vortices or the sub-vortices of multiple vortex tornadoes, those that are capable of generating those really strong winds. That's what we're trying to measure, those wind speeds inside using our armored vehicles, and now by launching model rockets into the tornadoes with trackable sensors in the nose cone. And now another question for everybody. You guys are nailing these questions. What are the ingredients for tornadoes? There are 4 very general ingredients needed for these tornadoes. Well, these are actually the 4 ingredients there. Number 1, an upper level storm system. Number 2 is wind shear. You need that changing wind speed and direction with height to cause that updraft to rotate and turn into a mesocyclone. The wind shear, especially right near ground level, about the lowest kilometer or even 500 meters near the ground, that low level wind shear is critical to tightening up the vortex below that mesocyclone. And of course, as we mentioned, we need instability, low level heat and moisture to fuel initially the development of these storms. And one thing I tell people all the time, no matter how perfect the environment is to produce tornadoes, you're not going to get a tornado if a thunderstorm fails to develop in that environment. So you definitely need a supercell storm to get a strong tornado, at least a supercell tornado. You can certainly get water spouts or land spout vortices without the presence of a massive supercell storm. But the really destructive tornadoes that impact so many people every spring and summer, those are caused by those supercell storms. And here are some of those ingredients in action. The upper level storm system, that's the jet stream, that image on the left with a tornado outbreak possible there. Just ahead of those troughs of low pressure or an upper level storm system, that's where the moisture gets pulled northward out ahead of it. That's where you can also get wind shear that's favorable for tornadoes. See that wind shear graphic right there? Imagine a surface wind that is nearly calm, and then just above that, you have winds that are ripping out of the south. So you have a calm wind at the surface. You can imagine 2 pieces of paper, one above it moving a lot faster than the one below it. That causes horizontal spin in the atmosphere that's basically invisible to the eye. But you get a lot of these horizontally spinning noodles out there created by horizontal wind shear. And then a thunderstorm develops, and that's that vacuum cleaner that we talk about, the mesocyclone above it. That's capable of flipping that horizontal spin into the vertical. We call that horizontal vorticity into vertical vorticity. And that very generally is how tornadoes form, but you need that warm, moist air at the low levels. The image at the right, that shows you very warm, moist air at the surface. That's a skew T that you can see there. The red line is temperature. The green line is moisture. And then notice how it's colder aloft. It really dries out just above the ground. So the key is to have that warm, moist air at low levels, often pumping northward from the Gulf of Mexico. Some other moisture and heat sources are the Corn Belt in the late season. But then if you get an upper level storm system, a cold, bowling ball of an air mass aloft that goes over top that warm, moist air. And those are the basics of instability. And as I mentioned, you need that supercell storm, that updraft. There's another mesocyclone that just came off of Raton Mesa there near the Colorado-New Mexico border. The right image is actually the track of a rocket that we launched inside the tornado, but the nose cone came out, the parachute deployed at about 400 feet above the ground. And when that parachute deployed, the trackable sensor in the nose cone was carried around inside the tornado. So you can see how it did 2 revolutions around the tornado and then entered the mesocyclone, or that tilted vacuum cleaner effect, and rode that mesocyclone all the way up to near 30,000 feet. And we were live streaming with that probe, so we could see what it was recording as it was going up. But then we lost signal when it got up to about 17,000 feet above the ground. We thought we were never going to see that probe again. This was from an EF4 tornado in 2019. So we posted on our social media accounts a picture of the parachute probe. And then in a matter of minutes, somebody actually found the probe in the front yard of a church there in Leavenworth, Kansas, over 30 miles away from where we launched it. But we retrieved that data. It showed you that it rode up the updraft of the tornado and then into that mesocyclone, which is basically the vacuum cleaner that intenses the vortex underneath it.
Hey, Reed, speaking of social media, good time to cut in. We got a few more things. You and I knew this would go long because you love talking about tornadoes. Just since we promised the selfie contest, in case anybody's got plans, we'll finish up for everybody out there. Reed's got plenty more. He's got more content, obviously, but I want to make sure nobody misses out on the opportunity to get that selfie with the prediction equipment. You just mentioned social media, and it was a perfect opportunity to do it. So for those of you who have a camera ready, make sure you grab it and put it together. And Reed, I know you've got some prediction equipment to go there. Remember, if you take this photo, upload it to Instagram, tag Reed TIMMER and tag Varsity Tutors, you'll be entered to win a weird, wild, wacky weather kit and a full year subscription to VT Plus. And for everybody who doesn't know what VT Plus is, highly suggest you check it out. All kinds of exciting classes on really any topic under the sun, whether it's academics, whether it's, fun stuff like tornadoes, storms, sharks, dinosaurs, space, or it's completely interesting things like just, learning to be better at Minecraft or learning magic tricks or anything like that. So want to make sure everybody's got a crack at that. Reed, let's get that picture going. So let's tell them a little bit about the prediction equipment, and then as soon as you're done, I know you guys have a lot of questions coming in. Keep them coming. We'll wrap up. Reed's got a few more sections he wants to hit, but I just didn't want anybody to miss out on the picture.
Thank you so much. So this piece of science equipment is what we try to deploy inside and around the tornadoes. And they measure that pressure fall in the middle of the vortex that drives that wind around it. They can actually measure some of those signals from a distance. And this is probably going to be deployed around a tornado coming up here in early February for the next storm system. But this is called the subsonic sensor. Never stop chasing.
All right. Huge thanks on the way out to everybody. We'll put up those tags so you can make sure you tag the right people on Instagram. Reed, sorry for butting in. I wanted to make sure if people have commitments in the next couple of minutes. So for everybody that wants to hang out, get some questions answered, I've got a couple minutes left because Reed has got some amazing stuff to talk about. So let's get right back into it. And Reed, you can pick up where you left off.
Yeah, sorry, guys. I lose track of time talking about these tornadoes. I think about them all day long, and I'm just honored to share some of this information with you guys. Now we're going to talk about outbreaks of tornadoes. And this is when those conditions come together. And the conditions we just talked about were wind shear, the upper level storm system, the low level heat and moisture. And when that upper level storm system is large enough or strong enough, those ingredients can come together over multiple states. And the outbreak that is the most infamous in recorded history in the US is the super outbreak of actually April 25th to 27th, 2011. April 27th was a big day with over 200 tornadoes in a single day. And usually the biggest, most substantial outbreaks like this happen in an area called Dixie Alley, which stretches from far east Texas across Louisiana, Arkansas, Mississippi, Alabama, Tennessee, Georgia, Kentucky. And the super outbreak in April 27, 2011 impacted all of those states. There were 3 EF5 tornadoes, numerous EF4s, EF3s. There were times when there were dozens of supercells with tornadoes on the ground. And all of those ingredients came together so perfectly that when a little cumulus cloud would develop and start to mature into a storm, the storm would produce a tornado before it was even producing rain. And that shows you just how efficient a storm can be at producing tornadoes when those ingredients come together. Sometimes these tornado outbreaks, the bigger ones, produce the most dangerous type of tornado, the nighttime tornado. And you can only see it when the lightning flashes, sometimes not even at all. This was one from an outbreak 2 weeks before the super outbreak, where over 100 tornadoes happened on April 15, 2011. Many of those were at night, very dangerous. And that's why you need to stay tuned to those watches and warnings when severe weather strikes, and have a NOAA weather radio with you as well, so it can alert you when severe weather develops in the middle of the night. A lot of times as well, these tornado outbreaks are associated with strong jet stream winds, so the storms can be very fast moving as well. And during outbreaks, there are numerous storms, sometimes wave after wave of supercell storms that can produce tornadoes. And this is some more images from the super outbreak showing you just how long track those supercells were and how many were happening. When I was chasing the super outbreak, I was overwhelmed because there were so many storms that were producing violent tornadoes. I was also incredibly concerned because I knew that people were in danger in the path of these storms. And that's why storm chasers are out there calling in that ground truth, working in tandem with National Weather Service forecasters and news media to try to let people know when dangerous tornadoes are happening so that they can warn people in the path of these storms. But 2011 was actually a La Nina year, similar to this year in 2021, opposite of an El Nino. It's characterized by cold water in the tropical Pacific. And usually in Tornado Alley and Dixie Alley, the most active springs happen just after La Nina winters. And that's what happened in 2011 with a very intense active jet stream, wave after wave going across the United States. You can see those purple tracks. Those are the EF5 tornadoes that happened during the tornado outbreak. And you can also see that very massive trough in that next slide. That's the upper level storm system that we were talking about. And this one covers the entire central US. Just east of this trough, conditions came together for tornadoes over multiple states, with tornadoes happening from Texas all the way up to New York State on that super outbreak. Well over 300 tornadoes, 21 states. Hopefully we never see something like this again in our lifetime, but definitely the most prolific tornado outbreak in recorded history. And now we're going to talk about those frightening forecasts. How do we get to within these tornadoes and forecast where those ingredients are going to come together? But first, I want to start off with a question. What is the difference between a tornado watch and tornado warning? Couple good answers coming in. Yep, no, when conditions are favorable for tornadoes, it's actually not a tornado warning. You actually need a tornado on the ground to get a tornado warning issued, or at least imminent development of a tornado. Tornado warnings are issued for the county level or even groups of counties out ahead of a supercell storm, or a tornado is imminent, or a developing tornado could be imminent. Usually those tornado warnings are issued based on Doppler radar detecting that rotation or the mesocyclone intensifying. Once the low-level mesocyclone reaches a point, it can develop tornado potential. The National Weather Service issues those watches and warnings. A tornado watch, though, is often issued a couple hours before a tornado happens, and that happens when conditions are coming together for the development of tornadic storms. One of the key agencies for forecasting severe weather is the Storm Prediction Center, or the SPC. They're the ones that issue those severe thunderstorm watches and the tornado watches. Mesoscale discussions are another a product that's issued by the Storm Prediction Center, basically a precursor to those watches. They also issue convective outlooks like this one, and this shows the infamous high risk. Those are issued ahead of those major outbreaks. This was actually the outlook that was issued ahead of the super outbreak, actually just that late morning, just before supercells were about to develop. And of course, the Storm Prediction Center nailed that forecast of the high risk, covering those areas where the ingredients were coming together for tornadoes most perfectly. And that happened over multiple states from Mississippi through Tennessee. And there were tornadoes throughout the slight and moderate risk areas on that day, all the way from the deep south through New York State. But the Storm Prediction Center, meteorologists, and storm chasers use what are called numerical weather prediction to predict where the ingredients are going to come together for tornadoes. These are supercomputers that ingest a bunch of data. They use equations of motion, a lot of calculus as well, to basically forecast these ingredients at time levels out. Some of the forecast models will predict in the long range. Some of the real fine scale models that are capable of predicting individual storms, those are run every hour in many cases. You can see CAPE, the upper left panel, that represents low level heat and moisture. The panels there with wind. The one on the top is the jet stream, the upper level winds. You also have measures of low level winds. Both measures of wind shear or changing wind speed and direction with height that can cause these storms to rotate. But these are just a few of the panels that we use to forecast severe weather. Tonight, there actually is a chance of severe weather and even tornadoes from northern Mississippi through central Tennessee. A couple of these ingredients are coming together. The heat and moisture, or the CAPE there, is a little bit limited, but the wind shear is very strong tonight. And sometimes when ingredients have an abundance, they can outweigh when other ingredients may be a bit lacking. In this case, we call this a high wind shear, low CAPE type situation. But I'll tell you what, the forecasting of these tornadoes is not easy. There are so many times that I go out there, I'll drive all the way across the country, get up there and have a completely blue sky bust. But usually that's a good thing because at least it means that that dark side that these storms leave behind is lacking during a bust. Now we go to one of the most important sections of this presentation, tornado safety. And we're going to begin with a question. When you hear a tornado siren, what should you do? I see some good answers coming in. A lot of it depends on if you have a storm shelter that's nearby. That's a great answer. But if you do hear a tornado siren or if a tornado warning is issued for your area, the easiest way to get that information is through a NOAA weather radio. Make sure your batteries are charged. And once you hear that warning, it's time to initiate your storm safety plan. You need to get into an interior room or closet. The best place to get during a tornado, though, is below ground in a storm shelter or a basement. But if you don't have a basement, an interior room or closet is ideal. Getting inside of a bathtub, covering yourself with mattresses is also a good plan. You want to try to put as many walls between you as the tornado as possible. Usually want to assume the tornado is coming from the west or the southwest. So usually the east or the northeast side, an interior room or closet in the house is the best. A mobile home is the worst place to be for tornadoes. So if you live in a mobile home, you want to involve a storm shelter or a community shelter in your safety plan. You want to factor in a little bit more lead time when you're looking at those alerts or tracking that severe weather. But really the safest place to be when a tornado strikes is below ground. And the key to surviving tornadoes is also learning about them, learning how to track them through radar. And I really hope that this presentation gave you at least a few tools that you can use to try to keep you and your family safe when severe weather strikes. But the most important thing is to not try this yourselves. I've been storm chasing for more than 2 decades. We have armored vehicles called the Dominators that keep us safe inside these tornadoes. You can see Dominator 1 at left. Dominator 3 at right there is the newest of these armored vehicles to do research. And these vehicles make it possible uniquely for us to get close to these tornadoes and maybe keep us safe from the very harsh conditions around it. But if you're in a regular vehicle, if you don't know how to storm chase, it can be very, very dangerous when you're out there in the field. And that's why you want to go with a veteran storm chaser, maybe sign up for a storm chasing tour and really learn the basics of visual observation of these storms before you head out there and storm chase yourselves.
Reed, a huge thank you, man. This was amazing. Thank you for the safety tips too. As fascinating as tornadoes are, they're also very dangerous. Like you said, even Storm Chasers code is be ready to go help people in need while you're out there. And so, really appreciate you mentioning that too. Fascinating to study, I'm sure. Fascinating to see. Even just the videos were pretty amazing. But it's really, really important that we got the safety out there. Hey, people have been asking some amazing questions, and I know we're already a little bit over time, but I think the most common ones, we'll try to get as many questions answered with one if we can, is as a combination of how did you become a storm chaser? What advice do you have for folks who would love to become a storm chaser or just a meteorologist? And basically, what is it like having a job as a storm chaser? So if you can answer as much of that as possible, I think we'll hit at least most people who asked a question or two. We'll be able to address most of them with that.
Well, when I grew up, I was into Science Olympiad as well. I collected insects for many years growing up. The long life passion that I always had were storms and severe weather. And growing up in Michigan, whenever severe thunderstorm warnings would get issued, I'd run around the house, couldn't contain my energy. And it was pretty obvious that I needed to do what I love for a living, which is my passion for weather. Whenever I say never stop chasing, it doesn't necessarily mean that literally, but never stop chasing what you're passionate about. And it's very easy to work hard and give it 120% effort day in and day out when you love what you're doing. But I decided to study meteorology at the University of Oklahoma. Once I got done with high school, I moved down to Oklahoma and then proceeded to study at the University of Oklahoma for the next 17 years. I went all the way through grad school, master's and PhD there as well. And I was storm chasing at the same time. So to be a storm chaser, you don't need a degree in meteorology, but you definitely do need to be passionate about it and need to understand how to forecast. And with severe weather, the easiest way to learn the basics of storm structure, go to your local National Weather Service office and take a Skywarn training course. Courses like this, of course, help out with storm structure and understanding how to forecast as well. And then you need a vehicle and go with somebody that knows what they're doing. And that's how you can really start to storm chase. Going to school as a meteorologist only helps to enhance those forecasting skills. Storm chasing helps put a visual part to what you're learning in the classroom. But really the storm chasers out there serve as the eyes in the field underneath these storms. So the more storm chasers out there, the better, because it's very difficult for a tornado to go unreported these days because there are so many eyes underneath the storm.
Well, huge thanks, Ray. I think some amazing advice in there. Definitely never stop chasing, regardless of what your passion is. I also think hopefully people got the message. You studied it for 17 years. So learning is the key to really understanding things, to being able to stay safe if your passion involves a little bit of danger out there, toward just opening your mind to possibilities that are out there. So Reed, huge thanks yet again. This was a blast, and you and I knew that it would go a little bit long because when you are passionate about something like this, you can't talk about it for just 45 minutes or so. So thanks everyone who hung on to get your questions answered. As promised, we are going to get the contest rules up on the way out so that you can, you don't have to spend 17 years at it, but you can learn anything with VT Plus. So if you can win that, and if you don't win, please check it out. Reed, we hope to see you again soon here. And, there's plenty of types of weather out there, as you know, even better than me. So we hope to see you soon. Everyone else, we hope to see you back. We've got all kinds of exciting StarCourses going on things from space to dinosaurs to everything in between. Too many to list. So we'll see all of you back here soon. Reed, same invitation to you. And thanks a lot, everybody.
Thank you.